Hello again. Welcome.
Hi, Mo.
Welcome to Nerd Rant, another one. One with a topic that, again, we scraped from the comments, and we are a bit unsure yet because we are not sure how to fill the allotted time for this Nerd Rant.
Yeah, but the right time to try to talk about it because of Houdini 19.
Yeah, maybe.
Because we saw XPBD being expanded on, and we wanted to talk about simulation frameworks.
Simulation techniques, maybe.
Simulation algorithms.
Whatever you want to call them.
Yeah, and by no means are we experts in this.
No.
It's just, why not talk about it a little bit? Maybe let me start with a little history or a little anecdote from my past, and that is when I was at Berlin to have a talk there. I met one TD from Pixar who was talking there too, and back then the Bullet engine got recently implemented inside of Cinema 4D, and I talked to him about simulation, and he never heard about Bullet back then. And I was like, yeah, look, have a look at Bullet. It's open source. It's quite fast, not the most precise out there, but have a look. And he did and was quite pleased. And that was before Bullet being everywhere. So, and today you have the feeling that Bullet is really dominating the rigid body realm. It's really everywhere. It's inside of Houdini. It's inside of Blender. It's inside of Cinema 4D. It's really used everywhere.
Did Bullet originate as a games simulation framework?
I think so. I think the idea behind Bullet is not to be very precise, but to keep interactive frame rates if possible.
How does it pull that off?
I don't know. Bullet can be quite fast, especially if you're going for the primitive collision types.
Yeah.
And but I'm not a game developer at all, so I cannot tell. It's just that I always enjoyed working with Bullet, sort of due to the speed. Everything that I used before, that was the inbuilt rigid body dynamics of Cinema 4D, the inbuilt rigid body dynamics of Houdini, was just slow. And Bullet was the first time, and I'm talking 2008 or so, the first time that I had the feeling, well, now I can actually look into simulation because it's fast enough not to shy me away.
I honestly must admit I didn't like Bullet quite that much because I found it a bit counterintuitive to set up sometimes.
And it is because of because Bullet is built around the idea that you use dedicated collision algorithms for the individual primitive types.
Yeah.
So if Bullet is colliding to spheres, it's using a different algorithm than colliding to cubes or to meshes.
Yeah.
And that was because they tried to make it fast. And of course, it's easier to collide to spheres than to meshes. And that is why when Bullet was introduced, you usually tried to approximate your geometry with a set of primitives to make it fast.
Yeah.
Well, yeah, that is cumbersome, and it still is, although today software does it automatically, sort of. Especially in Houdini, you have a lot of options to come up with combined or compound collision shapes and stuff. But all these very popular everything breaks down simulations are relying heavily on Bullet, I think, because that is really a lot of simulation. And especially with destruction, precision is not that important. It's about make stuff fall down. Nobody cares about if it's falling down that realistically.
Yeah.
And I think that is why the rigid body system is still inside of Houdini. Is it?
I think so, yeah.
Yeah, because it's just more precise. Yeah, especially with friction and stuff. Because Bullet tends to jittering, so even if stuff calms down, it's still never totally calm.
Never settles.
That's why you have this sleeping property in Bullet, where you just see if the velocity vectors are below a
threshold for a number of frames, and
force stuff to just not be simulated anymore.
Yeah. I mean, it works.
Smart. Yeah, it works, sort of.
I mean, you sometimes have to rely onto that approach in Vellum as well, with some simulations.
And why not? Nevertheless, Bullet is not that flexible. They do have implementation for soft bodies, but it's not particularly great.
Okay.
That's why most DCCs that integrated Bullet did not integrate the soft body part, but came up with a solution on their own. And that was that. And I'm not aware of a different rigid body solver being used at the moment. Of course, there's NVIDIA Physics.
Mm-hmm.
Very similar approach.
Mm-hmm.
It's not targeting precision, but speed. I saw some demos. Looked impressive because of speed.
Yeah.
Other than that, never used it myself.
No,
Did
cannot
you?
quote on it. No, cannot quote on it. I think it had the issue that it never really yielded quite the same results and with the same setup because...
But that is a problem that Bullet has too.
Yeah?
Yeah. It ends up differently. It's
Okay.
not replicable. Replicable?
Yeah.
Repeatable.
Repeatable, yeah.
That's
That's
the
what
word.
you're looking for, yeah.
Yeah. And that is, of course, a problem as soon as you're going for precise results. But as I said, if you just want to destroy a building, it probably doesn't matter too much if the piece of debris is ending up here or there.
Going here or there, yeah. That's right. So what's the next best alternative to it?
I don't know. I mean, regarding rigid bodies, I'm not aware of another very popular thing. I'm actually not sure what Unreal is using internally,
I have no clue.
nor what Unity is using.
Yeah.
They probably optimized for speed even more. I don't know. And that is, the purpose of these collision engines is a little different too, because it's mainly for the character not going through walls.
Yeah.
So it's, simple geometry most of the time, right?
Yeah, placeholder.
Yeah, and then there was this entire fluid movement where we had Lagrangian and Eulerian simulations.
Yep.
Smoke solvers
Yep.
popped up here and there and everywhere,
Yeah.
and particle fluids,
Yep.
SPH,
Yep.
with Houdini, of course, which had a very early SPH implementation, and then there was Real Flow simulating SPH. Regarding fluids or liquids, SPH was I didn't like it particularly because it could replicate this liquid splashy behavior quite well due to being particles, but it always tended to be very unstable. Forces added up and then stuff tended to explode.
Yeah.
So that is why I really did not like it too much. And back in the day when I used, I just had it.
Real Flow.
Real Flow, the Spanish fluid solution, it was just slow.
Yeah. Yeah, I remember that.
Yeah.
Yeah.
So that was not for me. And then the big revolution was starting when everybody started to use Flip. And today we have very solid Flip solvers like in Houdini.
Yeah.
I want at this point remember Nayad.
Nayad? Never heard of that.
That Nayad.
No. What is that?
Yeah, Houdini had a Flip implementation, and then some guys came up with a very, very nice node-based fluid solver network called Nayad, and it gained a lot of popularity very quickly.
Okay.
And was capable of huge simulations back then, and everybody was just excited. And it had a nice approach. And then it got bought by Autodesk.
Yeah, I was about to ask, did Autodesk just buy them?
Yes, Autodesk just bought them, and Nayad is basically the core of this Bitfrost thing that you now find in Maya.
Okay, I thought they just killed it.
No.
Okay.
They actually developed it further, and
Surprising.
it is inside of Maya now as Bitfrost. But I cannot tell how good it performs and how nice it is, actually, because since they bought it, I never touched it again.
Yeah.
But it started out being Nayad and being a big thing, even for Houdini TDs. Everybody started to use it, and everybody tried his hands or her hands on Nayad. Yes. And now, then Flip is still slow.
Yeah, comparatively.
Yeah. And that is the biggest problem with it, because, of course, it yields very realistic, interesting results. But I never particularly enjoyed doing Flip simulations just because it's so slow for my taste.
Yeah, it takes damn forever. And in general, I think that's why both you and me refrain from doing the traditional effects shots like the destruction or the huge ocean whitewater stuff rises out of the ocean.
Yeah.
Cliche sims that you see so often and that we get requested so often.
And rightfully so, because they look impressive. It's just nobody has the patience for this.
At least not the two of us. That is.
No, actually, no. It's just I'm having a hard time just waiting for simulations.
Yeah.
As soon as I have to split up simulation domains to distribute them to different machines to just simulate forever, that is just not my piece of cake.
Yeah, likewise, yeah.
And then there is gases, fluids, and I think
Yes.
you had quite some experience with these things, trying Embogen, trying turbulence, FD, and stuff like that.
Yeah, at some point. And I mean, once you understand the theory behind it, and there are very good master classes on that from, I think, Jeff Late,
Yeah, that was excellent.
who is an amazing lecturer when it comes to these topics.
I think it's called Building Fluid Solvers from Scratch.
Might be, yeah.
It's from 2000 and million years ago.
It doesn't matter because it teaches you the principles.
Exactly.
And once you understand those, you understand most of those pyro.
I'm trying to find the masterclass while you're talking.
Well, once you understand those principles, you understand most of how those pyro solver or those compressible fluid solvers work. And they all are similar in how they run their simulation, and even the output and the shading of the output is quite similar to that. You could boil it down to a few-step recipe in the end. The thing again with those solvers is they tend to get fun the faster you're able to run them, and to really be able to run them efficiently, you'll have to run them on the GPU, and the faster the better.
That is what I wanted to say. The GPU. Oh, Jesus.
Could you just shout at it?
Jesus Christ. What the?
That is YouTube advertising.
Yeah, YouTube. Hello. Here we are. Wait a second.
Oh, and also, I'll have to. So, lots of technical stuff happening here. I'll also have to prevent our display from switching off. Okay, so now we're back.
Yeah, I'm not
Advertising
sure.
stopped
I'm just
display
trying
there.
to find this masterclass.
It was building fluid solvers from scratch. Just if you Google for this.
No, I don't find it.
No, seriously? It doesn't matter. So the main thing is that with those types of solvers, they are easily parallelizable.
I did not find it because it is on Vimeo.
Okay, so
Here it is. 9
is
years ago. Watch this. It's excellent. Yes, sorry. So yeah, the GPU was a big thing with gas simulations.
Yeah, with compressible fluid solvers, so gas and fire solvers, because it's easily parallelizable. The only limiting factor here is for those solvers to be run efficiently, you have to have your whole simulation domain. That means your whole simulation volume in the VRAM of your GPU.
What about the going sparse with the volume?
It is hard to implement that on a GPU, as far as I understood from the people I've talked to. I am not sure if there are any solutions to this day that run sparse simulation on the GPU. Correct me if I'm wrong in the comments, but most solutions I know that work nowadays or that are in production nowadays use non-sparse volumes.
Mm-hmm. Because that will be sort of the holy grail of gas simulation, right?
Yes.
Multiple GPU. And I remember when Turbulence FD, one of the first to go to GPU, came out inside of Cinema 4D.
Yeah.
And it was, of course, not possible to create very large simulations due to VRAM restrictions. But the speed was just mind-blowing.
Yeah.
Especially with multiple GPU. And now we have that inside of Houdini. Does Houdini actually use multiple GPUs by now?
I'm not sure, I must admit. I'm not sure if it does for the sparse OpenCL PyroSolve, which is the quickest thing you could get nowadays in Houdini. I don't think so. But then again, what nowadays, as of beginning of November 2021, maybe not the cheapest, but the bestest hardware you could get for those simulations might be a 3090, which has 24 gigabytes of VRAM. And I think the VRAM is the limiting factor there, not necessarily the speed of the graphic chip. And you could also NVLink two 3090s together to get 48 gigabytes of VRAM.
Does that actually work for these simulations?
Haven't tried it yet. Maybe we should.
Because I
we should
tried
start
with
making
NVLink
calls.
with my 2080 Ti's, and it did not provide the speed up that I expected. Probably I did something wrong. I don't know.
But did it provide twice the VRAM?
Did not thoroughly test. I don't know. Yeah, VRAM is, of course, very helpful in many situations. Regarding simulation, that was important. Speaking of the GPU, we end up with the most modern simulation framework, if you ask me, and that is XPBD.
I'm not sure if it's,
Or PBD.
out of those that we touched so far, it might be the most modern, yes. Although it's not specifically on the GPU, although it originated as a games simulation framework.
Yeah. There was once this Verlet simulation paper
Yeah.
that described the physics inside of the game Hitman.
Yeah.
And I think that was one of the first papers outlining the ideas of PBD.
Might be.
And I always liked PBD a lot because
me
it's
too.
so straightforward.
Yeah,
Again,
it's just
not very
stupidly
precise,
simple.
but who cares about precision? Instead, it is just fast and simple to understand.
Yes.
Not only from a implementation perspective, but from a usage perspective. It's
absolutely.
just easy to use.
Yeah.
You have discrete things, you put attributes on the things, and you make it run.
Yeah. You have a bunch of points that are connected by lines, and you evaluate them.
And in theory, you can really simulate a lot of different phenomena with
Yes.
PBD. And that is very, very nice too, because you have just a versatile solver.
Yes, and it's been actively developed and actively researched. So the main research in XPBD, from what I get from the recent papers that have been published, is they look into new constraint types. So how to connect and how to evaluate the connections between those individual points. For example, Houdini 19 just recently released their fluid implementation.
Yeah.
The fluid constraints for XPBD is a few years old, I think, by now, the paper.
Yeah.
But the research by NVIDIA and by the two guys responsible for it mainly, which is Macklin and Müller, goes into researching new kinds of constraints. And I think the most recent one they put out is a volume conserving constraint, which can be really, pun, stretched to its limits. So you can really have like a flat sheet of your whole geometry, which then correctly expands into its previous volume without huge intersections and skittering.
Fantastic.
Just recently saw it on 2-minute papers, where I think it was advertised a bit misleadingly. It was advertised as this fast simulation technique, and that's XPBD, but that's just not what this paper was about. It was about the constraint, actually, that they just implemented and made accessible inside of XPBD nowadays.
That said, I get the impression that we can expect a lot more to come to the PBD framework, probably.
I hope so.
A lot of people consider this a holy grail or the standard tool, the most flexible solution to most simulation needs. I don't know. Now with the addition of rigid body-esque simulations, I'm not sure if you can use it for destruction. Probably not.
That addition, you mean by that addition you mean into Houdini.
Yeah.
So Houdini with H 18.5 or 19 has seen a new constraint type in XPBD, that is Vellum, that allows for rigid-ish body simulation. Not sure. I haven't tried it for destruction, but that would be an interesting use case, actually.
Yeah, probably.
I mean, by now in Houdini 19, you can do that stuff that we always dreamt about, like interaction between soft bodies and fluids. So just like soft body balls or balloons just floating up on top of a layer of liquid, stuff like that. Really impressive demo videos that came out with Houdini 19 that showed those capabilities.
Sounds great.
It is quick to evaluate. More and more components of it are being evaluated not only on the CPU but also on the GPU within Houdini. But again, I want to reiterate the main reason why I love XPBD, that is Vellum, is because it's absolutely simple. It is just points with a bunch of attributes and a bunch of lines connecting them.
And actually, I remember the name of the physics system inside of XSI that used this approach. It was called Lagoa Multiphysics.
I think I've heard the name, never used it.
It was pretty much similar.
Was it fast?
No, it was slow because it was implemented using ice nodes.
Oh, geez.
And they made it faster over time, but it just was not fast. It was very capable back then, but not fast. And regarding talking about not fast, there's one more solver that comes to my mind, and that is FEM.
I haven't ever touched it as far as I can remember.
The finite element method is very important for engineering.
Yeah.
It's used all the time to ensure the integral structure stability of a bridge, or optimize a piece of, I don't know,
Aerospace
leather,
part.
yes, because it is precise.
Yeah.
And in Houdini, you can use it to do very precise simulations.
Yeah.
Everybody knows these Aki worms crawling around using FEM.
Yeah.
Yeah. And I'm glad we have it. It's just I never use it due to the same reasons as with Flip. It's just too slow.
Yeah, it's
I
damn
cannot
slow.
stand it. It's just too slow.
Yeah. So no, I can't quote on it. I've never ever even touched it.
Yeah. But it is there, and if you need precision with anything deforming, it's probably the way to go.
Might be, although I think Vellum by now has decent volume conservatory or volume conserving constraints. And if you increase the solver steps, I think you will still have a faster solution than with FEM and get to a very similar
Nevertheless, I mean,
result.
Maybe we can put it that way. Start using Vellum, and only if Vellum fails you regarding precision for your particular use case, then you might consider using something else like FEM or Flip.
Yeah, I think that's the general good rule of thumb. And one thing that I want to elaborate on that came to mind when you were talking that Lagoa multiphysics was implemented using built-in ICE nodes. Vellum itself is implemented in Vex and OpenCL.
Mm-hmm.
So if you want to properly understand what's going on, you could crack open the solver and read the source code.
That's true. And if you need help on this, I even released a video ages ago about implementing a very simple position-based dynamics cloth solver from scratch with Vex. If you want to understand what's going on, maybe this video will help you.
Yeah, that's actually a good hint. Yeah, I totally forgot about that. Anything simulation framework-wise, simulation-ish that we need to add?
I don't know. I think it is. Here it is.
No, that's
Here it is. Implementing a position-based cloth solver from scratch. Very, very easy. So the bare minimum of a cloth solver necessary.
Whatever you describe as very
No,
easy.
that is basically simulation as far as we are concerned. Maybe we quickly hint on that there is simulation inside of Blender too.
Oh yeah.
Fluid simulation, that is, using MantaFlow, which is a more open source scientific simulation framework. So it's meant for scientific simulations, I think.
Mm-hmm.
And they've wrapped it for Blender.
Mm-hmm.
I tried it once. It's just inside of Blender without nodes, you don't have enough control over it. So I stopped quickly. And then
do you know what's the underlying simulation technique for MantaFlow?
Flip.
Okay.
And then you have Bullet inside of Blender, Bullet inside of Cinema 4D, and you have, how is it called in Maya, the unified simulation framework? I don't remember. It's it is PBD2.
Okay.
So Maya has a nucleus, I think.
Okay.
And
that is PBD
this is
as
just
well.
PBD, so it's comparable to Vellum, I think.
Yeah.
With particles and everything.
Yeah.
And one thing that came to my mind that I wanted to ask you about is recently, a year ago or two, I often heard about a program called Embergen.
Oh yeah, I tried that out for a few days or hours.
And this promised to be fast.
This was fast. I mean, I assume it still is fast. It is just what we talked about. It is like pyro simulation, that is compressible fluids on the GPU.
Mm-hmm.
Very fast, real time, basically. Issue I found back then is the resolution is lacking. So I have had a 2080, an RTX 2080 with, is that 8 gigabytes of VRAM? I'm not sure.
So.
That didn't allow past a volume resolution of, I don't know, 512 cubed, something like that. So it's rather low res. I mean, it's fun. And I think what they did, they mainly catered to gaming artists, and on the side also invited a few motion graphics artists who were not into crazy high-res simulations. And for games, I can see how and why that would work. And you would export an animated texture out of that and be done with your bullet hits, your torch that someone
Nozzle
lit.
fire. Or
yeah,
whatever.
Stuff like that. Or your magic appearing portal, stuff like that.
Yeah.
For that, it works really well. Has a really nice viewport renderer. easy to use, nice to use. It's just back then when I was trying it out, on the one hand, the resolution was lacking due to my low VRAM, and maybe they changed their algorithms. Maybe they support some more efficient memory management by now.
Let me look it up quickly.
But also, what in the end drove me away from it is that it's a standalone boxed solution. And if you want stuff to interact with each other, of course, you're better off setting up your scene in Houdini, where you can interact with everything.
Okay.
So yeah, that is.
But probably worth a look if you have some playtime.
So yeah, that is Django FX EmberGen. That's what it's called. So yeah, you see it here, game ready data. That's what they cater to. So they export those animation sheets for those types of explosions.
Okay, for that it's probably fantastic.
Yeah, again, cannot quote on the status of their solver and of their algorithms as of now.
Okay, so to quickly summarize before we wrap this up, with this beautiful burning fire in the background, simulations, a lot of fun, very important for a lot of effects that we do.
Yeah.
But for us too, it's always speed over quality.
And ease of use.
And ease of use, because if it's not art directable, if it's not easy to iterate, because it takes too long, it's not fun for us.
Yeah.
And that is why we strongly advise going the PBD route.
Yeah, that is Vellum. And if you're into Pyro, Houdini's Pyro, especially the minimal OpenCL, although not fully featuring everything that Houdini's Pyro offers, is very quick and very fun to iterate and play with.
Yeah.
And as for liquids, I mean, for small scale, there is Vellum. For large scale, you might not get around Flip at this point.
A lot of people enjoy using Flip. Not everybody's sharing this
this disdain for
large, long render times.
All right.
Perfect. So that was a simulation.
Rant, discussion, whatever you want to call it.
Thanks.
And with that, as always, it is cheers.
And goodbye.
See ya.